Maintainability. It is well known that the majority of the cost of software is not in its initial development, but in its ongoing maintenance, fixing bugs, keeping its systems operational, investigating failures, adapting it to new platforms, modifying it for new use cases, repaying technical debt, and adding new features. Yet, unfortunately, many people working on software systems dislike maintenance of so-called legacy systems. Perhaps it involves fixing other people's mistakes, or working with platforms that are now outdated, or systems that were forced to do things they were never intended for. Every legacy system is unpleasant in its own way, and so it is difficult to give general recommendations for dealing with them. However, we can and should design software in such a way that it will hopefully minimize pain during maintenance, and thus avoid creating legacy software ourselves. To this end, we will pay particular attention to 3 design principles for software systems. Operability: make it easy for operations teams to keep the system running smoothly. Simplicity: make it easy for new engineers to understand the system by removing as much complexity as possible from the system. Note, this is not the same as simplicity of the user interface. Evolvability: make it easy for engineers to make changes to the system in the future, adapting it for unanticipated use cases as requirements change. Also known as extensibility, modifiability, or plasticity. As previously with reliability and scalability, there are no easy solutions for achieving these goals. Rather, we will try to think about systems with operability, simplicity, and evolvability in mind. Operability: making life easy for operations. It has been suggested that good operations can often work around the limitations of bad or incomplete software, but good software cannot run reliably with bad operations. While some aspects of operations can and should be automated, it is still up to humans to set up that automation in the first place, and to make sure it's working correctly. Operations teams are vital to keeping a software system running smoothly. A good operations team typically is responsible for the following, and more: monitoring the health of the system and quickly restoring service if it goes into a bad state, tracking down the cause of problems, such as system failures or degraded performance, keeping software and platforms up to date, including security patches, keeping tabs on how different systems affect each other, so that a problematic change can be avoided before it causes damage, anticipating future problems and solving them before they occur, for example, capacity planning, establishing good practices and tools for deployment, configuration management, and more, performing complex maintenance tasks, such as moving an application from one platform to another, maintaining the security of the system as configuration changes are made, defining processes that make operations predictable and help keep the production environment stable, preserving the organization's knowledge about the system, even as individual people come and go. Good operability means making routine tasks easy, allowing the operations team to focus their efforts on high-value activities. Data systems can do various things to make routine tasks easy, including providing visibility into the runtime behavior and internals of the system, with good monitoring, providing good support for automation and integration with standard tools, avoiding dependency on individual machines, allowing machines to be taken down for maintenance, while the system as a whole continues running uninterrupted, providing good documentation and an easy-to-understand operational model. If I do X, Y will happen, providing good default behavior, but also giving administrators the freedom to override defaults when needed, self-healing where appropriate, but also giving administrators manual control over the system's state when needed, exhibiting predictable behavior, minimizing surprises, simplicity, managing complexity. Small software projects can have delightfully simple and expressive code, but as projects get larger, they often become very complex and difficult to understand. This complexity slows down everyone who needs to work on the system, further increasing the cost of maintenance. A software project mired in complexity is sometimes described as a big ball of mud. There are various possible symptoms of complexity: explosion of the state space, tight coupling of modules, tangled dependencies, inconsistent naming and terminology, hacks aimed at solving performance problems, special casing to work around issues elsewhere, and many more. Much has been said on this topic already. When complexity makes maintenance hard, budgets and schedules are often overrun. In complex software, there is also a greater risk of introducing bugs when making a change. When the system is harder for developers to understand and reason about, hidden assumptions, unintended consequences, and unexpected interactions are more easily overlooked. Conversely, Reducing complexity greatly improves the maintainability of software, and thus simplicity should be a key goal for the systems we build. Making a system simpler does not necessarily mean reducing its functionality. It can also mean removing accidental complexity. Mostly and Marx define complexity as accidental if it is not inherent in the problem that the software solves as seen by the users, but arises only from the implementation. One of the best tools we have for removing accidental complexity is abstraction. A good abstraction can hide a great deal of implementation detail behind a clean, simple to understand facade. A good abstraction can also be used for a wide range of different applications. Not only is this reuse more efficient than re-implementing a similar thing multiple times, but it also leads to higher quality software, as quality improvements in the abstracted component benefit all applications that use it. For example, high-level programming languages are abstractions that hide machine code, CPU registers, and syscalls. SQL is an abstraction that hides complex on-disk and in-memory data structures, concurrent requests from other clients, and inconsistencies after crashes. Of course, when programming in a high-level language, we are still using machine code. We are just not using it directly, because the programming language abstraction saves us from having to think about it. However, finding good abstractions is very hard. In the field of distributed systems, although there are many good algorithms, it is much less clear how we should be packaging them into abstractions that help us keep the complexity of the system at a manageable level. Throughout this book, we will keep our eyes open for good abstractions that allow us to extract parts of a large system into well-defined, reusable components. Evolvability, making change easy. It's extremely unlikely that your system's requirements will remain unchanged forever. They are much more likely to be in constant flux. You learn new facts, previously unanticipated use cases emerge, business priorities change, users request new features, new platforms replace old platforms, legal or regulatory requirements change, growth of the system forces architectural changes, etc. In terms of organizational processes, Agile working patterns provide a framework for adapting to change. The Agile community has also developed technical tools and patterns that are helpful when developing software in a frequently changing environment, such as test-driven development (TDD) and refactoring. Most discussions of these Agile techniques focus on a fairly small, local scale, a couple of source code files within the same application. In this book, we search for ways of increasing agility on the level of a larger data system, perhaps consisting of several different applications or services with different characteristics. For example, how would you refactor Twitter's architecture for assembling home timelines describing load on page 11 from approach 1 to approach 2? The ease with which you can modify a data system and adapt it to changing requirements is closely linked to its simplicity and its abstractions. Simple and easy to understand systems are usually easier to modify than complex ones. But since this is such an important idea, we will use a different word to refer to agility on a data system level: evolvability. Summary. In this chapter, we have explored some fundamental ways of thinking about data-intensive applications. These principles will guide us through the rest of the book, where we dive into deep technical detail. An application has to meet various requirements in order to be useful. There are functional requirements, what it should do, such as allowing data to be stored, retrieved, searched, and processed in various ways, and some non-functional requirements, general properties like security, reliability, compliance, scalability, compatibility, and maintainability. In this chapter we discussed reliability, scalability, and maintainability in detail. Reliability means making systems work correctly, even when faults occur. Faults can be in hardware, typically random and uncorrelated. Software bugs are typically systematic and hard to deal with, and humans who inevitably make mistakes from time to time. Fault tolerance techniques can hide certain types of faults from the end user. Scalability means having strategies for keeping performance good, even when load increases. In order to discuss scalability, we first need ways of describing load and performance quantitatively. We briefly looked at Twitter's home timelines as an example of describing load, and response time percentiles as a way of measuring performance. In a scalable system, you can add processing capacity in order to remain reliable under high load. Maintainability has many facets, but in essence it's about making life better for the engineering and operations teams who need to work with the system. Good abstractions can help reduce complexity and make the system easier to modify and adapt for new use cases. Good operability means having good visibility into the system's health, and having effective ways of managing it. There is unfortunately no easy fix for making applications reliable, scalable, or maintainable. However, there are certain patterns and techniques that keep reappearing in different kinds of applications. In the next few chapters, we will take a look at some examples of data systems and analyze how they work toward those goals. Later in the book, in part Roman 3, we will look at patterns for systems that consist of several components working together, such as the one in Figure 1-1. Walter L. Heimerdinger and Charles B. Weinstock, A Conceptual Framework for System Fault Tolerance. Technical Report CMU/SEI 92TR033, Software Engineering Institute, Carnegie Mellon University, October 1992. Ding Yuan, Yuluo Xinzhuang, et al. Simple testing can prevent most critical failures. An analysis of production failures in distributed data-intensive systems at 11th Usenix Symposium on Operating Systems Design and Implementation OSTI, October 2014. Daniel Ford, François Lebel, Florentine I. Papavisai, et al. Availability in globally distributed storage systems at 9th Usenix Symposium on Operating Systems Design and Implementation OSTI, October 2010. Brian Beach, Hard Drive Reliability Update, SEP 2014. Backplace.com, September 23, 2014. Laurie Voss, Oz, The Good, The Bad and the Ugly, blog.all.sm, December 18, 2012. Richard I. Cook, How Complex Systems Fail, Cognitive Technologies Laboratory, April 2000. David Oppenheimer, Archanaganapathy, and David A. Patterson, Why Do Internet Services Fail and What Can Be Done About It? At 4th Usenix Symposium on Internet Technologies and Systems Usits, March 2003. Michael Jorwitz, The Human Impact of Bugs, Jury.me, March 15, 2013. Rafi Krikorian, Timelines at Scale, at QCon San Francisco, November 2012. Greg Linden, Make Data Useful, Slides from Presentation at Stanford University Data Mining Class CS 345, December 2006. Gil Teen, HDR Histogram, hdristogram.org. Ben Mosley and Peter Marks, Out of the Tar Pit, at PCS Software Practice Advancement SBA, 2006. Rich Hickey, Simple Made Easy, at Strange Loop, September 2011.